Z substitution involves the substitution Z equals tan x over 2. So this involves the double angle formulae for sine theta or sine x and cos x. So if we draw a right angle triangle, angle is x over 2, tan is opposite over adjacent, so it's z over 1, and the hypotenuse will be root 1 plus z squared. From this we can then formulate expressions for sine x over 2. Sine x over 2 is sine's opposite over hypotenuse, so z over root 1 plus z squared, and cos x over 2 equals adjacent over hypotenuse, so it's going to be 1 over root 1 plus z squared. We're now going to use the double angle formula for sine x and cos x, sine 2x and cos 2x if you like. So sine 2x, recall, equals 2 sine x cos x. So because we are working with half angles here, so this will be 2 sine x over 2 cos x over 2. This will be sine 2 times x over 2. So just by applying the formula, 2 times x over 2 is just going to be x. So that's just going to be sine x equals 2 sine x over 2 cos x over 2, which, using the expressions that we've got for sine x over 2 and cos x over 2, sine x will be 2 times sine x over 2, which is z over root 1 plus z squared, times cos x over 2, which is 1 over root 1 plus z squared. So sine x equals, just multiplying all the way through the numerators and the denominators, we have 2z over 1 plus z squared. So that is the second formula we can use. And then likewise, cos 2x equals cos squared x minus sine squared x. There are two other formulae for cos 2x, so it doesn't really matter which one you choose to use to find the formula for cos 2x, for cos x rather, which is what we're going to do. So cos x will be cos squared x over 2 minus sine squared x over 2. So the square of this 1 over root 1 plus z squared will just be, the square of 1 is 1, and the square of root 1 plus z squared is 1 plus z squared, minus the square of sine x over 2 is the square of z, which is z squared, over the square of 1 plus, the square of the root of 1 plus z squared, which is just 1 plus z squared. So cos x equals, getting a denominator, a single fraction here, 1 minus z squared over 1 plus z squared. So these formulae here are what we are going to refer to when we see an integral involving sine x and cos x, and we can't use any other technique available to us. We're going to resort to this so-called z substitution. So evaluate the integral from 0 to pi over 2 of 1 over sine x plus cos x. Now just looking at this integral, you can try to evaluate this integral using any other technique, but you'll find that none of them work. So we can use the z substitution here, where we let z equal tan x over 2. And when we are writing down the formula, all we need to do is write down the formula for sine x over 2 and cos x over 2. Rather, the formula for sine x and for cos x. You will just need to remember these formulae that are blocked off here. You'll need to remember that. It won't be given to you on a formula sheet. It's unlikely to be on a formula sheet. So you'll need to remember these formulae. If you can't, then you can always go back to this, z equals tan x over 2, and derive the formula yourself. It might take a bit of time, but in preparation for an exam, if you need to, rather derive the formulae as opposed to trying to memorize them. So sin x is 2z over 1 plus z squared, and cos x is 1 minus z squared over 1 plus z squared. Okay, so this integral equals 0 to pi over 2 of 1 over sin x will be 2z over 1 plus z squared plus cos x, which is 1 minus z squared over 1 plus z squared. We also need to get an expression for dx. So we're going to use z equals tan x over 2. When we find the derivative of this expression, so dz will be the derivative of tan is sec squared x over 2, and the derivative of x itself, which is a half. Right, so you have to multiply that by a half, and that'll be dx. So dx will be 2 dz divided by sec squared x over 2. So dx will be 2 dz over sec squared x over 2. We're just going to put the sec squared x over 2 in here for now. We need to find a formula in terms of z for sec squared x over 2. So we go back to that triangle. So tan x over 2 z over 1. Now sec x over 2 is going to be hypotenuse over adjacent. So it's going to be root 1 plus z squared over 1, which is just root 1 plus z squared. And then when you square that, that square is going to take care of that root sign. So it's just going to be 1 plus z squared. So this will be, instead of writing sec squared x over 2, we're going to write 1 plus z squared. And now we've got everything in terms of z. We can then simplify and evaluate the integral. So we have 1 over, the denominator is 1 plus z squared. So we'll have 2z plus 1 minus z squared times 2 dz over 1 plus z squared. That equals integral 0 to pi over 2. We're going to flip this around now, so it's going to be 1 over 1 times 1 plus z squared over, so that is minus z squared plus 2z plus 1 times 2 dz over 1 plus z squared, which equals the integral from 0 to pi over 2. 1 plus z squared cancels with 1 plus z squared. This 2 we're going to take out of the integral sign, so just going to put it outside there. You have 1 over minus z squared plus 2z plus 1 dz. Before we continue, we also need to change the limits of integration, right? This is, at this point, the limits of integration are in terms of pi, right, which is got to do with your trig ratios. We don't have trig ratios here, we've just got z. So we are going to need to just change those limits of integration. So recall that z equals tan x over 2. So when x equals 0, then z equals tan 0 over 2, which is tan 0, which is 0. And when x equals pi over 2, z equals tan pi over 2 over 2, which is tan pi over 4, which is 1. So your limits of integration are 0 to 1. Now we need to get this expression here into a form that we can use. Now minus z squared plus 2z plus 1 does not factorize as we know it. So we're going to have to do some manipulation here. So we have minus z squared plus 2z and 1 we're going to write as plus 2 minus 1. We rearrange this such that we have 2 minus z squared plus 2z minus 1. All we've done is rearrange the terms. We have done nothing else. We're now going to factorize this expression here. So what we're going to do is take out a minus sign. We're just going to take out a minus 1. And we have z squared minus 2z plus 1. When you take the minus out, the minus 1 out, you're essentially dividing each term by minus 1. So every term in this bracket here just reverse the sign from this step over here. So minus z squared becomes z squared, positive 2z becomes minus 2z, and minus 1 becomes plus 1. And we can now factorize this because z squared minus 2z plus 1 is z minus 1 squared. And this is a form that we can use now because we have a squared term here. So this equals 2 times integral of 0 to 1 over 2 minus z minus 1 squared dz. Now we want to use a trigonometric identity here, so we are going to let z minus 1 be root 2 sine theta. Yeah, the reason we do that is because z minus 1 squared will then be 2 sine squared theta. So we will have 2 minus 2 sine squared theta. We can take out a common 2 and we have 1 minus sine squared theta, and that will equal 2 cos squared theta. 2 cos squared theta. So this will all equate to 1 over 2 cos squared theta, but we also need dz, right? Because we need a d theta here. So we're going to have to differentiate this function z minus 1 equals root 2 sine theta. So z equals root 2 sine theta plus 1. dz will be, root 2 is a constant, so it's going to be root 2. The derivative of sine theta is cos theta, and the derivative of plus 1, which is a constant, is going to be 0. So this is our expression for dz. So dz will be root 2 cos theta, and I should have put d theta there, d theta. We also need to look at the limits of integration as well. So this was z equals 0 and z equals 1. So z equals root 2 sine theta plus 1. So when z equals 0, we have 0 equals root 2 sine theta plus 1. Root 2 sine theta equals negative 1. Sine theta is minus 1 over root 2. So we're looking at an angle in the fourth quadrant. Right, so sine is negative in the third and in the fourth. So we're looking at an angle here, the negative acute angle. So theta will be 1 over root 2. Reference angle is pi by 4. If you work in degrees, it's 45 degrees. That's pi by 4 radians. So theta will be minus pi by 4. And when z equals 1, then we will have 1 equals root 2 sine theta plus 1. Root 2 sine theta equals 0. Sine theta equals 0, which means theta is 0. So we are going to be working from minus pi by 4 to 0. We can take out this half over here, so we have 2 times a half will just be 1. So we've got the integral from minus pi by 4 to 0 of, and the root 2 we should take out as well. So we'll have the root 2 on the outside, and then we have cos theta over cos squared theta d theta, which we can just write as 1 over cos theta. So that's root 2 integral from minus pi by 4 to 0. 1 over cos theta is sec theta. That equals root 2 times the integral of sec theta is ln sec theta plus tan theta. And we do not have an integration constant because we have a finite integral here. So that equals root 2 times ln sec 0 plus tan 0 minus ln sec minus pi by 4 plus tan minus pi by 4 equals root 2 times ln sec 0 is 1, tan 0 is 0, so 1 plus 0 is 1, and ln 1 is 0. We don't need the absolute value sign. We don't even need to write this term in because ln 1 is 0 minus ln sec minus pi by 4 cos minus pi by 4. Cos minus pi by 4 is in the fourth quadrant. Cos is positive there, as its reciprocal sec will be. Cos minus pi by 4 is 1 over root 2. So sec minus pi by 4 is the reciprocal of 1 over root 2, which is just root 2. Tan minus pi by 4 in the fourth quadrant. Tan pi by 4 is 1. In the fourth quadrant, where minus pi by 4 lies, tan is negative, so we'll have negative 1. So that will equal root 2 times minus ln, and root 2 minus 1 is a positive number, so we don't need the absolute value signs. Absolute value brackets, so root 2 minus 1 with round brackets. And I'm just going to clean this up by taking the minus outside. So it's minus root 2 ln root 2 minus 1, and that is the final answer. And determine the integral of 1 over 1 plus sine x. Okay, so we started off by saying that z equals tan x over 2, and then using the double angle formula for sine 2x, we found that sine x equals 2z over 1 plus z squared. And then dx equals 2 over 1 plus z squared dz. So this equals the integral of 1 over 1 plus 2z over 1 plus z squared times dx, which is 2 over 1 plus z squared dz. So that's the integral of, we're going to get a single fraction here at the bottom. So the LCD is 1 plus z squared. So we'll have 1 plus z squared plus 2z over 1 plus z squared times 2 over 1 plus z squared dz. That equals the integral of, going to flip this over, so it'll be 1 over 1 times 1 plus z squared over, in descending powers of z, so z squared plus 2z plus 1 times 2 over 1 plus z squared dz. 1 plus z squared cancels. We're going to pull the 2 out of the integration sign, so 2 times the integral of 1 over z squared plus 2z plus 1 dz. And that equals 2 times the integral z squared plus 2z plus 1. We're going to write as a perfect square trinomial, z plus 1 all squared. We can now use a trigonometric substitution. No, we actually don't. We don't need that. We can just write it as z plus 1 to the minus 2 dz. So that equals 2 times the integral of z plus 1 to the minus 2. We're going to add 1 to minus 2. We get z plus 1 to the minus 1, and then we divide by negative 1, so we're just going to put the minus sign there. And this is an indefinite integral, so we have to add the integration constant. So it'll be minus 2 z plus 1 to the minus 1 plus, and that equals minus 2 over z plus 1 plus c. This is not the final answer because our z that we chose was tan x over 2, and the problem was in terms of x, so we can't leave it in terms of z. It's minus 2 over z is tan x plus 2, sorry, tan x over 2 plus 1 plus c. That is the final answer. Okay, so z equals tan x over 2, sin x equals 2z over 1 plus z squared, cos x is 1 minus z squared over 1 plus z squared, and dx equals 2 over 1 plus z squared dz. So that equals the integral from 0, and in fact, straight off the bat, we need to change the limits of integration here. So 0 to power by 2. So when x equals 0, we have z equals tan 0 divided by 2, which is tan 0, which is 0. And when x equals pi by 2, z is tan pi over 2 over 2, which is pi by 4, and tan pi by 4 equals 1. So the limit of integration would be from z equals 0 to 1, and that's going to be 1 over 1 plus sin x is 2z over 1 plus z squared. Cos x is 1 minus z squared over 1 plus z squared. And that is dx is 2 over 1 plus z squared dz. So getting a denominator at the bottom, 1 plus z squared, have 1 plus z squared plus 2z plus 1 minus z squared times 2 over 1 plus z squared dz. Okay, so the limit, not the limit, the integral from 0 to 1, 1 over, we have z squared minus z squared, cancel, so it's 1 over 2z plus 2 over 1 plus z squared times 2 over 1 plus z squared dz, and then we're going to flip this around. So we're going to have 1 plus z squared over 2z plus 2. 1 plus z squared cancels with 1 plus z squared. We can then take out a common 2 at the bottom. So 2 times z plus 1. The 2's are going to cancel, and that will give us the integral from 0 to 1 of 1 over z plus 1 dz, which is the integral of 1 over z plus 1 is just ln z plus 1, and this is evaluated between 0 and 1. So that's going to be ln 1 plus 1 is 2, minus, we don't need the absolute value brackets, so just ln 2, minus, when z equals 0, we'll have just ln 1, so the final answer is ln 1 is 0, so we just have ln 2. Okay, again, z equals tan x over 2. We've only got cos x here, so we're only going to worry about cos x. So cos x is 1 minus z squared over 1 plus z squared. Rather dx equals 2 over 1 plus z squared dz. So that equals the integral from 0 to pi by 3. In fact, we're going to not use those limits of integration because we need to. This pi by 3 and 0 relates to the trig ratio cos. So when x equals 0, then z equals tan 0 over 2, which is tan 0, which is 0. And when x equals pi by 3, then z equals tan pi by 3 by 2, which is pi by 6. 10 pi by 6 in degrees, that's tan 30. Tan 30 is 1 over the square root of 3. So the limit of integration will be from 0 to 1 over root 3 of 1 over 3 plus 2 times cos x is 1 minus z squared over 1 plus z squared, and dx is 2 over 1 plus z squared dz. Okay, get a denominator. We get 3 plus 2 minus 2z squared over 1 plus z squared times 2 over 1 plus z squared dz. That's 1 over 3 times 1 plus z squared plus 2 minus 2z squared over 1 plus z squared. We're going to tip this over, so we're just going to write the 1 plus z squared at the top there and remove this denominator, and that's times 2 over 1 plus z squared dz. The 1 plus z squared will cancel, so that equals integral from 0 to 1 over root 3, 1, 2 over 3 plus 3z squared plus 2 minus 2z squared dz. The integral from 0 to 1 over root 3 of 2 over z squared, 3 plus 2 is 5, dz. I'm going to pull the 2 out of the integration. That's 1 over z squared plus 5 dz. We are now going to use a trigonometric substitution, so we're going to let z be root 5 tan theta, so that z squared will be 5 tan squared theta, and z squared plus 5 is therefore 5 tan squared theta plus 5, which is 5 times tan squared theta plus 1, and tan squared theta plus 1 is sec squared theta, so it's 5 sec squared theta. dz, when we differentiate, dz will be root 5 sec squared theta d theta. We also need to establish the limit of integration, so when z equals 0. We have 0 equals root 5 tan theta. That implies that tan theta equals 0, which implies that theta equals 0. And then when z equals 1 over root 3, we have 1 over root 3 equals root 5 tan theta. So tan theta equals 1 over root 15, which means that theta equals tan to the minus 1, 1 over root 15. And that's how we're going to leave it. This is not the kind of answer you want to evaluate. So you just leave it in that form. So 2 times integral from 0 to tan to the minus 1, 1 over root 15, or arctan 1 over root 15, however you want to see that, of 1 over z squared plus 5 is 5 sec squared theta, and then dz is root 5 sec squared theta d theta. Sec squared theta will cancel, and we're left with 2. We can actually take out all of these constants, root 5 over 5. So we'll have 2 root 5 over 5 times integral from 0 to tan to the minus 1, 1 over root 15. And then all we have left is 1 d theta. So 2 root 5 over 5 times the integral of 1 with respect to theta will just be theta, and that's evaluated from 0 to tan to the minus 1, 1 over root 15. So it's 2 root 5 over 5 times tan to the minus 1, 1 over root 15 minus 0, which is just 2 root 5 over 5 tan to the minus 1, 1 over root 15, and this is the final answer. So z equals 10 x over 2 cos x equals 1 minus z squared over 1 plus z squared, and dx equals 2 over 1 plus z squared dz. And the limit of integration would be x equals pi over 3 to x equals pi over 2. So z equals tan pi over 3 over 2, which is pi by 6, and that is tan 30 degrees, which is 1 over root 3. When x equals pi over 2, then z will be tan pi over 2 over 2, which is pi by 4, and tan pi by 4 is 1. So the limit of integration will be between from 1 over root 3 to 1, and the integral becomes 1 over 1 minus z squared over 1 plus z squared. Dx is 2 over 1 plus z squared dz. So we can get a denominator over here, single fraction. So we have 1 plus z squared minus 1 minus z squared times 2 over 1 plus z squared dz. That's the integral from 1 over root 3 to 1. We're going to flip this over, so we'll have 1 plus z squared over z squared minus z squared would be 2z squared, and 1 minus 1 is 0, times 2 over 1 plus z squared dz. 1 plus z squared will cancel, 2 will cancel, and we have the integral from 1 over root 3 to 1. And the only thing we have is 1 over z squared dz. So it's the integral from 1 over root 3 to 1 of z to the minus 2 dz. When we integrate that, we will have negative z to the minus 1, which is minus 1 over z, and that is from 1 over root 3 to 1. So that's going to be, when z equals 1, we'll have negative 1 minus, then we'll have minus 1 over 1 over root 3, which is going to be minus root 3, and then minus times a minus root 3. This will give us minus 1 plus root 3. And that's the final answer.